Let's talk about Newton's law of cooling for a moment. Bless you. So the whole idea of Newton's law of cooling is that, do I want to start there? Yeah, I kind of do. Is that what we're saying is that the rate of change of the temperature of an object, so dt, where T is for temperature, capital T is for temperature, lowercase t is for time. The rate of change of the temperature of an object is proportional to the difference in the temperature of the object and the temperature of the surroundings. In fact, and I apologize just in general in this class. I teach 2 sections of this class, so it's really hard for me at this point to remember what I've said in what class versus the other class. Like I'm just not sure what I've said here or there. So I'm going to say something that I know is important. I don't think I've said it here yet, but I just want to remind everybody or show everybody that when you're solving, I should say, yeah. So to solve the differential equation, not that we're doing that in these classes, but I just want to point out, to solve the differential equation, dy dt equal to k times y, where the rate of change of your population is proportional to the population size. What's interesting about this, I think, is that the solution is the model of exponential growth, is y equal to c e to the kt. Which makes some amount of sense if you think about it, right? If your rate of growth is in direct proportion to how many people there are, then the more people there are, the faster the growth rate is, which leads to an exponential growth model. The reason I'm mentioning this, though, is because, in fact, we can even check this as a solution here. If you actually take the derivative of this, the derivative of c e to the kt is, in fact, c e to the kt times the derivative of kt, which is k, and that's exactly y times k, or k times y. The reason I'm actually mentioning this is because this is actually probably the most important differential equation you will see in 17b and 17c. This is the one that like kind of a lot of what we do in 17c is based on, is this particular fact that the derivative of the function equaling a multiple of the function leads to the function being c e to the kt. That said, this is essentially the same sort of situation here. We're saying the derivative of a thing is a constant multiple of essentially that thing. Yeah, you got this other temperature over here, but it's not that big a deal. So what this ends up leaving us with is that this temperature minus the surrounding temperature ends up equaling exactly some c e to the kt for exactly the same sort of reason. If you took the derivative of both sides of this, and I'm going to point out that in this equation, capital T is your function, lowercase t is your variable. Anything else, k, c, and ts are all constants. So we differentiate both sides just to check that we're actually getting what we think we should be getting. The derivative of the left-hand side is going to be dt minus 0 equal to the derivative of this, which is going to be c e to the kt times k. But again, since c e to the kt is equal to T minus the surrounding temperature, this is really just equal to T minus the surrounding temperature times K. Exactly the differential equation that we started with. So I just want to really show you that, oh yeah, this solution, which we haven't quite finished with yet, but this solution to your differential equation actually is a solution. If you take the derivative of both sides, you end up getting the differential equation that kind of started this whole process. So that's kind of the big picture Newton's law of cooling. We can then take this equation and usually solve for temperature. So if we solve for T, we end up getting the surrounding temperature plus C e to the KT. You could do more here, but I don't think you really need to. So there's like a more refined version of this formula, which says that C is actually like, I don't actually remember what it is. It's the difference between your surrounding temperature and initial temperature. But I think that's way more worth to remember that. I would remember this if I had to remember anything. And I would actually probably add it as T of T. So there's the formula for Newton's law of cooling. So we're going to use that to answer a question. A thematically appropriate question since it's the month of Thanksgiving. So here's our question that we're going to look at. A turkey is 185 degrees. That's probably too hot if you want it to taste good when taken out of the oven. But definitely a safe temperature to cook a turkey too. And placed in a room in a 75-degree room. Question part A. If, I think there's only a part, no, this part B. Cool. If the temperature of the turkey is 150 degrees after 10 minutes, what is the temperature after 30 minutes? Like, how long is it going to take till we can eat some turkey? So we're going to start with the general setup. We know that the temperature at time t is equal to the surrounding temperature, which is 75 degrees, plus some initial C value times e to the kt. And what we're going to do is we're going to use these two data points, just like any exponential growth or decay problem. You're almost always going to have two data points, a time and a temperature, and another time and another temperature. Just like for other ones, you have like a time and a population and another time and a population. As usual, I'm going to make a table. I've got my times and my temperatures. I know that in the beginning, when the turkey comes out of the oven, the temperature is 185 degrees. And then 10 minutes later, the temperature of the turkey is 150 degrees. Using those two things, we can figure out what our C and our K values are. So let's plug in this first. This first one's a little bit easy, but again, it's not quite as simple as just regular C to the KT. So we plug in 185 for the temperature and 0 for the time. We get 185 equals 75 plus C e to the K times 0, or in other words, 110 equals C. So yeah, C is usually your initial temperature minus your surrounding temperature, but I never remember that, so I just do it this way. One less thing to remember. And then we're going to refine our model. We're going to say the temperature at time t is now 75 plus 110 e to the kt. And then we're going to plug in our other data point. So we're going to say the temperature is 150 equal to 75 plus 110 e to the k times, and the time is 10 minutes later. And that's going to allow us to solve for k. So subtract 75. 75 equals 110 e to the k times 10. Divide by 110. So you have 75 over 110 equal to e to the 10k. Take the natural log of both sides. You could probably reduce this fraction to what? I don't know, 15 over 22. So the natural log of 15 over 22 equals 10k. And finally, 1/10 natural log of 15 over 22 is equal to k. So finally, now we can write our model. Let's write another piece of paper here. So our temperature at time t is going to be 75 plus 110 e to that number k, 1/10 natural log of 15 over 22 times t. And now the question that we wanted to answer that was asked at the very beginning here is, what is the temperature of the turkey after 30 minutes? So we're going to set time equal to 30 and solve for the temperature, which isn't too terrible. So I'm going to just plug in 30 and get T of 30 equal to 75 plus 110 e to the 1/10 natural log of 15 over 22 times 30. We could do one slight simplification here to make this a little bit less terrible to plug into a calculator. We could write this as 75 plus 110 e to the 1/10 times 30 is just 3. So you can write this as 3 times the natural log of 15 over 22. But then to get anything else, you really have to plug it into a calculator. Did I bring a calculator? Maybe. Yes, I did. Let's see what we've got here. So let's see, I'm going to do 110 times e to the, where's my e button? Problem with using calculator. Oh, there we go. E to the 3 times natural log of 15 over 22. And we're going to get about 34.8, and then we're going to add 75. So about 109 degrees. Probably cool enough to eat. You gotta let your meat cool down before. Again, right, these are made up numbers. They're probably not actually super realistic. Although I tried to make it somewhat realistic, but like this is just an example of what you could use Newton's law of cooling for. Newton's law of cooling is also the reason, like, if you want to cool down a drink that you've just like brought home from the store, it makes more sense to put it in the freezer than in the fridge compartment, because the bigger the difference in temperature, the faster the rate of change of the temperature. Any questions about that? Yeah. TS is the temperature of the surrounding environment. So in this case, the surrounding environment was 75 degrees because that was the temperature of the room you put it in. Yeah. Should we do another one? Should we not do it? Yeah, okay. Let's do one more. So this is a pretty typical example of a dead body problem. Okay, so let's just write down the pertinent information here. Number 2. Police discover a dead body at 10 p.m. So we have a body at 10 p.m. The temperature is 87 degrees Fahrenheit. In a room that is 70 degrees. 1 hour later, the body is now 86 degrees. When did the murder happen? Sorry, I didn't say it was murder. It was a murder. When did the murder occur? Or what time did the murder occur? Same sort of setup. So, and again, I'm hiding some information that we'll come back to in a minute here, but we will write down what we know. So we know that the initial observation at 10 p.m., the body temperature was 87 degrees. 1 hour later at 11 p.m., the body temperature was 86 degrees. And I want to know, what do I want to know? I mean, I want to know when the murder occurred. So I want to know at what time the body temperature was a typical body temperature. And what do we generally assume a normal body temperature is in Fahrenheit? 98.6. 98.6 is the general assumption. I don't know if that's actually correct, but it is what people usually default to, unless they're told something else. So we're really wondering what time it was when the body was 98.6 degrees. So here's what we're going to do, and what I always do for these kind of problems. I'm going to say that the initial observation was time equals 0. So right here, 10 p.m. is time equals 0. 11 p.m. is time equals 1 hour later. And when we answer this question here, we should get some negative time. Right? So if we're going to find time, let's pretend like time ends up being like -8 hours. That means the murder occurred 8 hours before 10 p.m. or 2 p.m. So that's the idea. This is the easiest way to make these problems work, I think. So usual setup. We have that the temperature at time t is equal to the surrounding temperature plus C e to the kt. The surrounding temperature is 70 degrees. That's going to equal 70 degrees plus C e to the kt. I should be able to remember what C is, but I just can't. I think C here should be 87 minus 70, 17. But let's plug it. It's easier just to not have to try to remember another thing. So I plug in 87 for the temperature and 70 for the surrounding temperature and C e to the k times 0. Then yeah, I'm going to get 17 equal to C. Great. And then we update our model. Now it's the temperature at time t equal to 70 plus 17 times e to the k times t, which makes sense if you think about it, right? Because if you plug in t equals 0, you get 70 plus 17 times 1, which is 87. So that seems totally legit. And then we're going to plug in our other data point. So at 11 p.m., the temperature is 86 degrees. That's going to equal 70 plus 17 times e to the k times time is 1 there. And then we solve for k. So we're going to get, let's see here, 86 minus 70 is 16, equal to 17 e to the k. 16 divided by 17 is equal to e to the k. So the natural log of 16 over 17 is equal to k. So now we've got our fully fledged model. So the temperature at time t is equal to 70 plus 17 e to the natural log of 16 over 17 times t. And now we're going to set that equal to the temperature of the body when it would have still been alive. So we're going to set that equal to 98.6 degrees and solve for t. And solving for t is pretty much the same process as solving for k. You isolate the e to the whatever thing, and you take the natural log of both sides, and then you solve for whatever. So here we're going to subtract 70 from both sides. We get 17 e to the natural log of 16 over 17 times t equal to 28.6 divided by 17. So e to the natural log of 16/17 times t is equal to 28.6 over 17. Take the natural log of both sides, so we're going to get the natural log of 16 over 17 times t is equal to the natural log of 28.6 divided by 17. And finally, t is going to equal the natural log of 28.6 over 17 divided by the natural log of 16 over 17. And I will point out that this answer is going to be negative, because the natural log of 28.6 over 17 is positive because that number is larger than 1, but the natural log of 16 over 17 is negative because the thing you're taking the logarithm of is smaller than 1. Let's do it. So I'm going to have the natural log of 28.6 divided by 17 divided by the natural log of 16 divided by 17. I get negative 8.58. So that means we have to go back about 8.5 hours. So 10 p.m. minus 8.5 hours approximately is going to be about 1:30 p.m. And technically it's 8 points, so it would be like at 1 and 42 hundredths of an hour, but let's just approximate it. 0.5. Cool. That's kind of a fun problem. Yeah. So what you could do here if you wanted to is you could totally rewrite e to the natural log of 16 over 17 times t as e to the natural log of 16 over 17 to the tth power, and then you can write that as 16 over 17 to the tth power. You do have to have that raised to the power of t there. Yeah. This one's a little nicer than a lot of them because you don't have anything dividing the natural log here. But like in the previous one, just to kind of point out here, in the previous problem, where we have this, you could rewrite this as well, but it's even kind of grosser. This here, this e to the, I'm going to write the 1/10 times t as t over 10 times the natural log of 15 over 22. You can rewrite this as e to the natural log of 15 over 22 to the t over 10, which is then just 15 over 22 to the t over 10. Kind of terrible though. What this actually does show us though is the nature of how this exponential growth or decay works. So here's kind of a truism. Actually, I should write this down. I should not just say things. So when we talk about exponential growth or decay, there's 3 ways of phrasing this that are all equivalent that I just want you to hear. So one way of saying that something is growing exponentially is you say it's growing exponentially. So we can say like the population is growing exponentially. Another equivalent way of phrasing this that might not sound the same is the relative growth rate is constant. Another way of saying this that might not sound the same is population grows at a rate proportional to the population size. And there are three different equations or three different ways of writing the equations that represent these things that all are the same equation. So this first equation here, population is growing exponentially, is your typical y equals c e to the kt. This last one here, the population grows at a rate proportional to the population size, is the one I talked about in the beginning, where I said, oh yeah, the rate of change of the population is a multiple of the population size. These equations are essentially the same, right? This equation here is the solution to this differential equation here. And finally, the relative growth rate being constant, we can just say that we're really just taking this equation here and saying that k is equal to dy dt divided by y. This brings up a really good point. And again, please stop me if I've said this in this class before. Last class, did I ask about like, so let's say the population is growing at like 5,000 people per year. Is that meaningful? Well, it depends. It depends on where you are, right? Are we in Davis? Yeah, that's a lot of people in Davis. If you're growing at 5,000 people per year per a population of 60,000 people, that's a lot. Or are we in New York City? Growing at a population, growing 5,000 people per year per 5 million people is not particularly meaningful. So that's why the growth rate here doesn't matter. Your dy dt, not so important. Your relative growth rate, your rate of growth divided by your population size, that's what is a more telling piece of information here. So when we say that the relative growth rate is constant, that exactly means you have exponential growth. Or decay, right? Every time, really, when I say growth, you should hear or decay every time, because really it's a growth or decay, same kind of thing. So then what I was trying to get back to was the fact that the kind of telltale thing, and I should say there's one more thing to say here. The time it takes for the population to multiply by any particular constant, like for the population to double, triple, whatever multiplication factor you want to pick, is constant. So like when we talk about having exponential growth, exponential decay, we talk about the half-life, which is just the constant amount of time it takes for the population to cut in half, or for the radioactive material to cut in half. We're talking about the doubling time. Like we often say, oh yeah, here's a population that's growing exponentially, and it takes 30 years for the population to double. That constant amount of time and that multiplication factor are the kind of the key things here. So in this previous problem, when we were talking about the simplification here, what I just want to point out is writing this way tells me that it takes 10 minutes for the amount of stuff to multiply by 15 over 22. Every 10 minutes, I'm going to multiply by another 15 over 22. If t is equal to 10, I get 15 over 22 to the first. If t is equal to 20, I get 15 over 22 squared, which is 15 over 22 times another 15 over 22. Let's do one more problem, and then I promise we'll move along. So, and we're not going to do all of it. We're just going to see this one thing. So let's say we're looking at some radioactive material. That's right, in a place where you can see things. Radioactive, I can spell, yes. Material. We have a 600 gram sample. And every 5 hours, and 5 hours later, we have 400 grams remaining. How much will we have in 15 hours? And although we could set this up as a y equals c to the kt thing here, we actually don't really have to. And here's what I wanted to show you. Again, using my time and my amount, I know that time equals 0. I have 600 grams. I know that 5 hours later, I have 400 grams. And I know that every time I have a 5-hour increase, I'm not going to decrease by 200 grams. That's not the right relationship. It's not a linear relationship. You can't ever get down to zero, right? With exponential decay, right? If I did that, if I decreased by 200 grams every 5 hours, in 10 more hours, that would be at 0 grams, which is not the thing that works, right? If your equation is y equals c e to the kt, I want to point out that this is always, always, always greater than 0, as long as c is positive. This can't ever equal 0. But 5 hours later, it's not that I'm going to decrease by 200, it's that I'm going to multiply by the same factor. So to go from 600 to 400, I multiply by 4 over 6, which is 2 over 3. And the same thing's going to happen here. 5 hours later, I'm going to multiply by another 2 over 3 and get 800 over 3. And another 5 hours later, I'm going to multiply by another 2/3 and get 1600 over 9. And I could find a decimal, but I don't really care to. I guess we could, just to satisfy our curiosity. Whoops, that's not the right way to divide. About 177.8. Or we could have done this the long way, right? We could have said y equals 600 e to the kt, plugged in this data point, 400 equal to 600 e to the 5k, and then solve for k and gotten 2/3 equals e to the 5k, natural log of 2/3 divided by 5 equals k. And then when we rewrite our model here, we get y equal to 600 e to the natural log of 2/3 over 5 times k. And if we rewrite it in the way that we were talking about, not that I think you necessarily should do this, but it does show you that if we rewrite this as, let's see, it's going to be e to the natural log of 2/3 to the, that's a t, by the way, not a k, sorry, to the t over 5. That's going to be 2/3 to the t over 5. What this is showing me is that every time t increases by 5, I'm going to multiply by another 2/3, which is exactly what we saw over here. So I could plug in t equal to 15 and get y equal to 600 times 2/3 to the 15 over 5, which is exactly 600 times 2/3 to the third, which is going to exactly get me over to 1600 over 9. Right, it's going to be 600 times 8 over 27. You can cancel a 3 here and a 3 here. You get 200 times 8 over 9, which is exactly 1600 over 9. Sorry. So just to drive the point home one more time, exponential growth, exponential decay, it's the amount of time, like some set amount of time is how long it takes for the whole population to multiply by the same factor. So in this case, every 5 hours, we're multiplying by 2/3. In the previous examples, every 10 minutes, we were multiplying by something gross, like 15 over 22. Yeah.
For every problem like this, can you just like draw out the table and multiply by the?
Yes, but this only works if the amount of time you're at. So like if I had said how much radioactive material was there 9 hours after the process started, it's not going to work out so nicely. So that's when you really need to use this over here. But if you are lucky enough to be given an amount of time that is an integer multiple of the amount of time elapsed in your first kind of 2 data points, then yes, you can do this nicely. All right, let's move along. Section 3.7, talking about all these derivatives of logarithmic and inverse tangent function stuff. Cool. I think we talked about the derivative of the log and the derivative of inverse tangent already. Let's refresh our memories. Here. So this is a reminder. The derivative of the natural log of x is 1 over x. And the derivative of the inverse tangent or the arctangent of x is 1 over x squared plus 1. And whenever I see formulas like this, I immediately want to think of the chain rule version. So if the derivative of the natural log of x is 1 over x, that also means the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. And similarly, the derivative of the arctangent or inverse tangent of some stuff is going to be 1 over the stuff squared plus 1 times the derivative of the stuff. So 2 more rules to add to our long list of derivative rules. And that's kind of the last of them. I think there's no other like derivative rules we learned. I think we've learned how to differentiate every kind of function we're going to be able to differentiate, I think. So now what? Well, now we can ask more interesting derivative questions, like, for example, if f of x is equal to x cubed times the natural log of 1 plus e to the x, let's find the derivative of that. Okay, so I'm just going to use my usual rules. I've got x cubed times the natural log of 1 plus e to the x, so I'm going to use the product rule. So I'm going to do 3x squared times the other function untouched plus, and then we switch it up. We leave the x cubed alone or untouched, and we take the derivative of the natural log of 1 plus e to the x, which is going to require the chain rule. I can't stress enough how much I'm saying this in my head. I see the natural log of some stuff. I tell myself, great, the derivative of the natural log of x is 1 over x, so the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. That is literally the words that are playing in my head. So I see the natural log of some stuff. I'm like, cool, the derivative is going to be 1 over the stuff times the derivative of the stuff. If I wasn't asked to simplify this, I'd probably just leave it as is. But if I was asked to simplify it, I would rewrite this right-hand piece as x cubed times e to the x divided by 1 plus e to the x. To make it look a little nicer. But that's all the simplification you can do here, really. Let's look at a few more things. Oh, I forgot there are. Okay, so I didn't really lie, but there are a couple more functions we technically haven't talked about taking the derivative of. They're really just other versions of the natural log function. Let's talk about 2 more things real quick. So just to add to our list here, I will remind you also that the derivative of e to the x is e to the x, and the derivative of the natural log of x is 1 over x. And then something interesting happens if we pick a different base for these exponential or logarithmic functions. And again, I don't recall. I feel like we talked about taking the derivative of something like 6 to the x. Yay, nay, maybe. So here's how we would do it. Well, here's how I would do it. How would I do it? There's so many ways to do it. I would probably do it this way. I would write it as the derivative of e to the natural log of 6 to the x. And then the x comes down. Is really equal to the derivative of e to the x times natural log of 6. Great. I know how to take the derivative of e to the stuff. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. So we're going to get e to the x times natural log of 6 times, here's the place where people often have a little bit of a challenging time. What's the derivative of x times natural log of 6? Good question. Better question. What's the derivative of 5x? Right. What's the derivative of x times 3? Right. Even though I wrote it kind of in an atypical way, it doesn't matter if you have x times 3 or 3 times x, it's still the same thing and it still has the same derivative. Okay, one more to make it weird. What's the derivative of x times pi? Pi. So as long as you have x times a constant, the derivative is just that constant. Well, natural log of 6 is a constant. It's not a nice constant, but there's no x's in natural log of 6. If there aren't any variables in there, it's a constant. Even if it's like, well, we'll say that in a second. So the derivative of x times natural log of 6 is just 1 times natural log of 6. And then we should rewrite this because e to the x times natural log of 6 is just e to the natural log of 6 to the x, which was just 6 to the x that we started off with. So this is really just 6 to the x times natural log of 6. So the more general rule for differentiating some exponential function whose base isn't e is that the derivative of b to the x is equal to b to the x times the natural log of b. And if your base happens to be e, well, great, that still works. The derivative of e to the x is e to the x times natural log of e, and natural log of e is just 1. And then there's a very, very nice correspondence between how changing the base for the exponential function works and changing the base for the logarithmic function works. So I'm going to say it now because I want to write it right here, but then we'll show it. So just like here, where having a different base made me multiply by the natural log of that base, if I take the derivative of log base b of x, I'm not going to divide by the natural, or sorry, I'm not going to multiply by the natural log of b. I'm going to divide by the natural log of b. So I'm going to get 1 over x times the natural log of b. Why is that true? Well, there's a couple ways to see it. How should we see it? There's so many ways we could do it. Let's talk about doing it this way. So, yeah. So there's a couple ways we can go here. I can probably put this in here. Yeah. So let's say we want to take the derivative of y equal to log base b of x. You could use a change of base formula, but I'm going to do something different. I'm going to rewrite this. I'm going to rewrite it as the exponential equation. What's my base? What's my power? What's it equal to? The only thing is left, x. And then we're going to take the derivative of both sides. Implicitly. All right, we talked about implicit differentiation, where y is a function of x. So then if we take the derivative of both sides, the derivative of b to the y is going to be, well, the derivative of b to the x is b to the x times natural log of b. So the derivative of b to the stuff is going to be b to the stuff times the natural log of b times the derivative of the stuff. And the derivative of x is 1. And then we can solve for y prime. So y prime is going to equal 1 divided by b to the y times natural log of b. But b to the y is equal to x. So we really end up getting that y prime is equal to 1 over x times natural log of b. Cool. So the way I really do remember this is that for exponential functions, we end up multiplying by the natural log of the base. And for logarithmic functions, we end up dividing by the natural log of the base. That's how it always works. So for example, if I wanted to find, say, the derivative of 4 to the x cubed plus sine of x, I know the derivative of e to the x cubed plus sine of x is going to be e to the stuff times the derivative of the stuff. I know if I change my base, I'm just going to toss in an extra natural log of that base. So here it's going to be 4 to the stuff times the derivative of the stuff, which is 3x squared plus cosine of x, times the natural log of my base, which is the natural log of 4. Oops, that's what I meant to do. Cool. And then in a similar way, we could ask, what's the derivative of the log base 6 of x to the 5th plus cotangent of x? Well, same idea. I know the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. So if I have a base 6 there, I'm just going to throw in a natural log of 6 in the denominator. So I know it's going to be, I'm going to write this in kind of a terrible way because it's the way I think of it. It's 1 over my stuff times the derivative of the stuff, which is going to be 5x to the 4th minus cosecant squared of x, and then divided by natural log of 6, or multiply by 1 over natural log of 6. This is probably the most unwieldy way you could write it. It'd be much, much nicer if I would just write it as 5x to the 4th minus cosecant squared of x, divided by x to the 5th plus cotangent of x, all times natural log of 6. That's much better. But I really like to think of the fact that I'm doing 1 over the stuff, then multiplying by the derivative of the stuff, and then at the very end, I'm also dividing by the natural log of my base. So I wouldn't. I prefer to memorize like the basic for very oh my god, the words. I prefer to think of the basic version of the derivative formulas. Like I'm remembering that the derivative of the natural log of x is 1 over x. And then the derivative of the natural log of some stuff is 1 over the stuff. And times the derivative of the stuff. And then the derivative, and then if I have a different base, I'm just adding in or dividing by the natural log of that base. You could write down a formula though. You could say, great, the derivative of b to the x is b to the x times natural log of b. The derivative of log base b of x is 1 over x times natural log of b. And then you could also write down the chain rule versions. The derivative of b to the stuff is b to the stuff times the derivative of the stuff times the natural log of b. And the derivative of log base b of some stuff is going to be 1 over the stuff times the derivative of the stuff, and then divided by the natural log of b. But in my opinion, if you know this version of the formula, you also know this version of the formula. Because you all know how to replace x with some stuff, and then at the end of the day, multiply by the derivative of the stuff. Exactly. Whenever you're replacing x with some stuff, you know you have to multiply by the derivative of that stuff. Cool. What time is it? All right, we got plenty of time. So then we like to do terrible things like the following. Let's say I want to find the derivative of the function f of x equal to the natural log of x cubed times sine of x times the square root of x to the 4th plus 8. Nobody wants you to do this like it's written. You don't want to do it like it's written. I don't want you, if I'm grading it, for you to do it like it's written. We want to simplify this expression before we take the derivative. Specifically, we want to use the properties of logarithms to break this apart into many smaller, simpler logarithms that are easier to take the derivatives of. What I mean here is that we should rewrite first. So we're going to rewrite as f of x equal to the natural log of x cubed plus the natural log of sine of x plus the natural log of, I should write this as x to the 4th plus 8 to the 1/2 power. And again, before I take the derivative, I should actually simplify this one step further. I should rewrite this as 3 times the natural log of x plus the natural log of sine of x plus 1/2 times the natural log of x to the 4th plus 8. So that now, when we take the derivative, it's much less terrible. Our derivative f prime of x is going to be 3 times the derivative of the natural log of x is 1 over x, plus the derivative of the natural log of some stuff is 1 over the stuff, so 1 over sine of x, times the derivative of the stuff, which is cosine of x, plus 1/2 times the derivative of the natural log of x to the 4th plus 8 is 1 over x to the 4th plus 8, times the derivative of x to the 4th plus 8, which is 4x cubed. So you can really save yourself a lot of grief if you take the time to simplify a logarithmic expression first. Let's do another one. Why don't you guys try this one? So I want you to differentiate the natural log of the quotient x to the 4th times tangent cubed of x divided by the cube root of x to the 5th plus 2. You should definitely break this apart into how many logarithms? 1, 2, 3, or 4? Show me on your fingers. I think 4 is one too many. You can only get 3. So when I'm thinking about the number of logarithms I'm going to get, I'm looking at the number of factors that are in my expression. And I see 3 factors, an x to the 4th, a tangent cubed, and a cube root of some stuff. We can't break this into 2 different pieces here. So try breaking this up into 3 logarithms before you differentiate it. Bring down your powers, and then after you've brought down the powers, then take the derivative. All right, let's talk through the simplification. So here's what I'll say very generally. When you have a logarithm of a quotient of some things multiplied together, divided together, all the things on top end up with positive logarithms. All the things on the bottom end up with negative logarithms. So I'm getting the natural log of x to the fourth plus the natural log of tangent cubed minus the natural log of the cube root of x to the fifth plus 2. Which I think is a step you could totally, I think you could skip this first step of doing one, breaking it up, and just jump straight to saying, oh yeah, all the top factors get positive logs, all the bottom factors get negative logs. And then we bring down the powers, so we get 4 natural log of x plus 3 natural log of tangent of x minus 1/3 natural log of x to the fifth plus 2. You can't break up x to the fifth plus 2 anymore, right? You can't, there's no good rule for the logarithm of something added together. It's only for logs of products or quotient, not for sums or differences. So then we take the derivative. That's why I've written this derivative thing every time, because I still have to take the derivative. I've just been simplifying. Now we're going to get 4 times 1 over x plus 3 times 1 over tangent of x times the derivative of tangent of x, which is secant squared of x, minus 1/3 times 1 over x to the fifth plus 2 times the derivative of x to the fifth plus 2. And that's it. So when you have a logarithm of something gross, the intention of the person writing the problem is for you to make it a simpler problem before doing any differentiation. That's a that's a good rule of thumb in general, whether it's a logarithm or something else. If you can significantly simplify a function or something before taking the derivative, that is usually in your best interest to do so. All right. I lied before. I forgot about one kind of function that we haven't taken derivative of yet. So let's say we want to find the derivative of x to the x power. So we can't use the power rule here because it's not x to a constant. And we can't use the exponential rule here because it's not a constant to the x. When you have a variable in both your base and your exponent, you're kind of stuck. So this is a problem that requires the process of logarithmic differentiation. So here's what we're going to do. Whenever you see something where you have, or more generally, the derivative of some function of x raised to another function of x, the process is the following. Start by writing whatever your function is as y equal to that. You have to have an equation here to make this really work. Then we don't want to have a variable in our exponent. And the most common way of getting variables out of exponents is by taking the natural log of that thing. So we're gonna take the natural log of both sides of this equation. We're gonna have the natural log of y equal to the natural log of x to the x, so that we can then bring the x down in front of the logarithm there. We have the natural log of y equal to x times the natural log of x. After we've gotten our variables out of our exponents, then we're going to differentiate both sides implicitly. So on the left-hand side, I know the derivative of the natural log of x is 1 over x, but the derivative of the natural log of y, or some stuff, is 1 over the stuff times the derivative of the stuff. So the derivative of the natural log of y is going to be 1 over y times dy dx, or y prime if you prefer, whichever way you like to write it. On the right-hand side, I'm always going to have to use the product rule, because I brought down a variable in front that's multiplied by the natural log of a variable. So you have a function of x times a function of x. So it definitely is going to require the product rule. So it's going to be 1, which is the derivative of x, times, leave the other thing alone, plus x times the derivative of the natural log of x, which is 1 over x. Now we're going to solve for dy dx. So multiply both sides by y. And it's always going to be multiplied by y. Because whenever you do this, you're always going to have a natural log of y on the left. And we take the derivative of both sides, it's always going to be a 1 over y times the derivative equal to that. And so you're always going to multiply by y at this step. So you're going to get dy dx equal to y times all of this. And I like to simplify this here if I can. That's just the natural log of x plus 1. And then finally, we should replace y with what we know y is equal to. So we're going to have that dy dx is equal to x to the x times the natural log of x plus 1. And that's the process of logarithmic differentiation. And it's pretty much always these 4 or 5 steps. So whenever you see something where your base and your exponent are both functions of x, this is when you want to do this process. Let's look at another example. Let's say we have, and I'll point out, so I will say, I did write this one in maybe the cruelest way possible, because I wrote it in a way that didn't remind you that you need to start off by writing y equals x to the x. So in the textbook, I'm looking here, they say something like, for the example, the way this is phrased in the textbook for problems 33 through 41 is use logarithmic differentiation to find the derivative of the function of y equal to x to the sine of x, for example. Right, so they're doing you the kindness there of telling you, oh yeah, you need to start off with y equal to the thing you want to take the derivative of, so that then it's easier to recognize that you have to take the natural log of both sides of this expression, of this equation, I should say, not expression. But you might not see that on the exam, right? On the exam, it might just be like, they might phrase it as differentiate x to the sine of x. And then you have to have the wherewithal to be like, oh yeah, I need to write down y equals x to the sine of x, and then take the natural log of both sides, and then do all this other stuff. Let's do it. So now we're taking the natural log of both sides. Natural log of y equals the natural log of x to the sine of x. The reason we did that was so that we can bring down the sign. Because the natural log of y equal to sine of x times the natural log of x. And then we're going to differentiate both sides. And just like on the previous page, we differentiate both sides. The left-hand side, you're always going to get 1 over y times y prime. The right-hand side, you're always going to have to use the product rule. So we're going to get the derivative of sine of x, which is cosine of x, times natural log of x, plus, switch it up, leave the sine of x alone. Derivative of the natural log of x is 1 over x. I think you can do this next step, these next two steps in one personally, like you can multiply both sides by y and also replace y with what it's equal to. But if that's not comfortable, it's totally fine. We can say y prime is going to equal y times all this stuff. And the only real simplification I can do here is write sine of x times 1 over x as sine of x over x. And then finally, replace y with what y is equal to, which is x to the sine of x. So my derivative here is going to be x to the sine x times cosine of x times natural log of x plus sine x divided by x. There is a terrible formula you can try and memorize. I have never memorized it. It's not worth taking the time to put one more thing in your head. It is much, much better to memorize this process.
Sine x over x is 1.
Thank you for asking the question. I was hoping someone would ask. No, you cannot. And here's why. Sine x over x isn't equal to 1. If you think about the graph of sine x over x, right, it has lots of values. It's actually never equal to 1. But what we're thinking here that that's kind of making us think that is if you were taking the limit as x was approaching 0 of sine of x over x, then you could replace it with 1. But we're not taking a limit here, so we definitely cannot do that. Thank you for asking that. I was hoping someone would ask. Yeah, so yeah, when you see sine x over x, you only get 1 if there's a limit as whatever the stuff is approaching 0. There was something else. Sometimes people will ask you to use logarithmic differentiation even when it's not some variable raised to another variable power. Again, looking at these problems in the textbook, yeah, here's an example. I don't know if I love this process personally for this, but since you were asked to do it, we should at least do one of them. So let's say we are given y equal to, yes, this is gross, sine squared of x times tangent to the 4th of x over x cubed times x squared plus 1 to the 5th. I mean, it's problem slightly different than problem 35 in the textbook. Use logarithmic differentiation to find y prime. Technically, you could do this one without logarithmic differentiation. It would be terrible, but you could use the quotient rule and the product rule for the top and the bottom and the chain rule for each of those product rules, but it'd be really, really gross. So sometimes when your derivative is really gross and there's a bunch of things that are either multiplied or divided together, right? It's not really good for any other situation. If you have a bunch of things multiplied or divided together or raised to powers, logarithmic differentiation is an acceptable and useful tool. So let's do it. And take the natural log of both sides. Natural log of y equals the natural log of all this garbage. Sine squared of x times tangent to the 4th of x divided by x cubed times x squared plus 1 to the 5th. And then unlike the previous problems where we're then bringing down the power of whatever our variable is, here we're going to break this up as much as we can. So here's my first step. I'm going to break up the right-hand side as the natural log of sine squared of x plus the natural log of tangent to the 4th of x minus the natural log of x cubed minus the natural log of x squared plus 1 to the 5th power. I think that is a reasonable first step. If you don't like that first step, oops, sorry, you could have started off by first just writing it's the natural log of the top stuff, sine squared x times tangent to the 4th x, minus the natural log of the bottom stuff, which is x cubed times x squared plus 1 to the 5th. And then when we break this up, it's the natural log of sine squared plus the natural log of tangent to the 4th. And when we break this up, it's minus parentheses the natural log of x cubed plus the natural log of x squared plus 1 to the 5th. And that minus sign distributes, and you get a minus sign in front of both of them. Or as I said before, all the factors in top get logarithms with positive coefficients. All the factors in the bottom get logarithms with negative coefficients. It always works out that way. And then we bring down the powers. You have the natural log of y equal to 2 times the natural log of sine of x plus 4 times the natural log of tangent of x minus 3 times the natural log of x minus 5 times the natural log of x squared plus 1. And then we finally are in a place where it's good to differentiate both sides. So we're gonna differentiate both sides. On the left, we still get 1 over y times y prime. On the right, we get 2 times 1 over sine of x times negative times positive cosine of x, plus 4 times 1 over tangent of x times secant squared of x, minus 3 times 1 over x, minus 5 times 1 over x squared plus 1 times 2x. Finally, since I'm almost out of room, I am just going to write, so I'm going to multiply both sides by y, but I'm actually going to replace y with what we know y is equal to. So y prime equals y times all this stuff, which I'm going to simplify a little bit. Cosine x divided by sine x is cotangent x. We have 2 times cotangent of x. Unfortunately, secant squared divided by tangent doesn't really have a nice simplification, so we're just going to write it as 4 secant squared of x over tangent of x minus 3 over x minus 5 times 2x is 10x over x squared plus 1. All that times its initial y thing, which was sine squared of x, tangent to the 4th of x over x cubed times x squared plus 1 to the 5th. So there's your really terrible derivative. It's probably better than doing it the other way. Yeah. I will point out, if you did it the other way, your answer would look quite different, because your answer would just be one fraction. It'd be really gross fractions, but just one fraction. Whereas this, you'd have to do some manipulation to get them to look like the same answer, but they are the same answer. Cool. See here, what else do I have in mind here? Oh yeah, we didn't do any arctangent one. We should do some of that. Let's. So there's one thing that I saw that looked kind of cool. Yeah, it's actually, so there's this question. It is a homework question, but I think it's worth looking at anyway. So it's number 52 from this section. It was to find y prime if x to the y equals y to the x. So if they're saying find y prime, we are assuming y is a function of x. Always, right? If they say find the derivative of y, and I know they didn't write it, but when they say this, what they mean here is dy dx, the derivative of y with respect to the independent variable x. That means we get to assume y is a function of x. So when we differentiate this, x is good old independent variable x, and y is some stuff. So anyone have a guess as to what I might want to do first with this equation, x to the y equals y to the x? Take the natural log of both sides, right? We got things in exponents that we don't want there, so we take the natural log of both sides. We bring down the power. It sounds like we're like, fight the power, bring down the power. We're bringing down the powers. So y times natural log of x equals x times natural log of y. And when we differentiate, we're going to have to use the product rule on both sides, because both sides are a function of x times a function of x, and a function of x times a function of x. So the derivative of y is dy dx times, leave the natural log of x alone, plus y times 1 over x equal to, now we do the derivative of the right-hand side. So product rule over here, the derivative of x is 1, leave the other piece alone, plus, now you switch it up, leave the x alone, multiply by 1 over your stuff times the derivative of your stuff. This looks a little bit more like, oh, sorry, apologies for using mixed notation here. I use dy dx here and y prime that is kind of terrible. I should have just stuck with one of them. Let me grossly change this to a dy dx. Sorry, it's terrible. Question?
Would it be more messy if you took the derivative when the y's were on the or y's and x's were on the same side or on their respective side?
So to do that, I'd have to do division, right? And that, so you could totally first say, I'm going to have the natural log of x divided by x equal to the natural log of y divided by y. The problem here is that I would rather not use the quotient rule. I think it's going to get messier if I introduce the quotient rule. So then from this step here, we're going to collect our terms that have dy dx, just like kind of a typical implicit differentiation problem. bring them all to one side, bring everything else to the other side, factor out your dy dx and solve for it. I think I can stop there though. I don't think I need to show you the rest of that. You all can figure that out for yourself. Good problem though. I like that problem. All right, what else have I got to say in the last 10 minutes? Oh, we should, yeah. So, right, I'm not gonna see you all till Tuesday. So let's talk about the next section. Unless I should ask, are there any other questions about this section 3.7, which is logarithmic differentiation and arctangent stuff? Sure, yes. So here's what I think so I believe what they want you to do, and I think this problem is actually easier than it looks. So they want you to show the limit as n goes to infinity of 1 plus x over n to the nth power, yeah, is equal to e to the x. Now, what I'll say is later on, when we learn about L'Hopital's rule, we'll show that we'll do this for real. But for now, what I think they're really banking on you doing is using something that was already in the textbook, specifically in section 3.7, box number 5, I don't know, or box number 6, actually. So here's box number 6 in the textbook in section 3.7. It's that the limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to e. Or as I would say, the limit as some stuff goes to infinity of 1 plus 1 over some stuff to the exact same stuff is equal to e. Doesn't matter if the stuff is n or n plus 1 or n divided by 3, right? As long as the stuff here matches the stuff there, it's totally good. So I'll just point out, you could have said the limit as n goes to infinity of 1 plus n divided by 3 to the, sorry, that's blah. Oh my gosh, James, sorry. Let me try that again. 1 plus 1 over n divided by 3 to the n divided by 3 power is equal to still e. As long as the stuff that's under the 1 here matches the stuff that's to the exponent here, and the stuff is going to infinity, and if n's going to infinity, n divided by 3 is still going to infinity, then everything's okay. Okay, so here's what they want us to do here. You need to take this side and make it look like that. Kind of. So here's what we're going to do. We're going to rewrite this as the limit as n goes to infinity of 1 plus, I'm going to write this as 1 over n over x. Just to make it look like I'm used to seeing it, right? X divided by n is the reciprocal of n divided by x. And then in the exponent here, well, I really, really wish I had n divided by x. So I'm going to make it happen. I'm going to say I have n divided by x times x. Technically, I didn't change anything. I just made it look gross. But are things still the same? Yes, they are. Right? 1 over n over x. This whole thing here is really just the same as x over n, which is what I had right there. And this whole thing here is really just n. Okay, but now we're going to do the fun part here. Then we're going to rewrite this as the limit as n goes to infinity of, I am going to write this now as 1 plus x over n. No, I'm going to leave it as is. 1 plus 1 over n over x to the n over x. And when you have powers multiplied together, you could write those as powers to powers. And now, two things. Thing one, well, actually, yeah, no, one thing. This x doesn't care what n's doing, right? X is independent of n. So I could actually bring this limit inside of these brackets and write this as the limit as n goes to infinity of 1 plus, I am going to write it as x over n here just to make it look normal, to the n over x power, all raised to the x power. Now let's ask the important question. Is the limit of this e? Well, let's see. I have 1 plus 1 over some stuff to the stuff. Is m over x getting infinitely large? It is. So it works. I have some stuff that's getting infinitely large. I have 1 plus 1 of that stuff to that stuff's power. And as far, or in fact, if you really want to kind of do it in a, I don't know. No, I don't really like that. I think you can just say this is equal to e to the x. That's the gist of this problem. I think that's what they intend for you to do. Is they intend for you to use this box number 6 fact that the limit as n goes to infinity of 1 plus 1 over n to the n is e, and then essentially just raise both sides to the x power. Kind of weird, kind of fine. All right, the other thing I was going to talk about, but yeah, let me just give you a brief idea of what's happening with section 3.8 linear approximations. I'll give you one very quick example. Linear approximation is just a terrible name for the equation of the tangent line. So for example, and here's kind of the most typical example. I want to use a linear approximation to estimate the square root of 10. So here's the idea. We're going to graph the function, the square root of x. You're not usually going to graph it, but we're going to graph it this time. So we're going to graph f of x equal to the square root of x. So here it is. And let's say 10 is right there. What we're really going to do is we're going to find a place that's close to 10 that's much easier to plug into your function. What's the number that's really close to 10 that's easy to take the square root of? 9. So what we're really going to do is we're going to find over here at 9, I'm going to make it a little far apart. We're going to look there. We're going to find the equation of the tangent line. And then say, great, well, if I plug in 10 to that tangent line, that y value there is going to be pretty close to the square root of 10. So that's going to be my L of 10, my linearization evaluated at 10. So I'll say this again, finding a linearization of a function at a particular point is just finding the equation of the tangent line at that point. So what we're going to do here is we're going to find the linearization, just fancy word for equation of the tangent line, of f of x equal to the square root of x at a equal to 9. We usually call it a for some reason that I don't really know why we call it a, to be honest. Great. So we're just going to do the usual thing. It's going to be y minus the y coordinate equals the slope times x minus the x coordinate. The x coordinate's 9. What's the y coordinate if x is 9? Right. So my a is 9. My x is a is 9. x1, I should say. My y1 is my f of a, which is the square root of 9, which is 3. And how do we find the slope of the tangent line? Take the derivative. So my slope here is going to be f prime of a, which is f prime of 9. Sorry, my a and my 9 look a little too similar there. And the derivative of the square root of x, well, if f of x is the square root of x, f prime of x is 1 over 2 root x, or 1/2 x to the negative 1/2. So then f prime of 9 is going to be 1 over 2 times the square root of 9, which is 1/6. So then the equation of our tangent line is going to be y minus 3 equals 1/6 times x minus 9. And typically, when we write this specifically for a linearization, we isolate y, but we don't do anything more, meaning we're going to add 3 to both sides, and we're going to stop right there. We are not going to distribute the 1/6 and add up the terms to get the y-intercept. And this is what we call our linearization. The linearization, again, it's really just the equation of the tangent line at a particular point is going to be 3 plus 1/6 times x minus 9. And then to answer the question of approximating the square root of 10, we're going to plug in 10. So, right, this is an approximation of the square root of x. It's a better approximation when we're close to 9. If you move far away from 9, you can see this is they're gonna have much more separation, and it's not very good if you get too far away from 9. So then the square root of 10 is approximately L of 10. And by the way, this is why we don't simplify this. It's much easier to plug in 10 here than to plug in 10 to like a simplified version where you have to do more calculation. Here I just could say, oh, it's 3 plus 1/6 times 10 minus 1, 10 minus 9, which is just 3 plus 1/6. Or if you like decimals, 3.16 forever. You pull out a calculator, you can see that the square root of 10 is actually approximately, super annoying, 3.1622. So look, we had a pretty good approximation, right? The first 2 decimal places were right on, and the third decimal place is where we diverge. They have a 2, we have a 6. So I will just say finally, the general idea here, or the general formula for a linearization of f of x at the point a comma f of a is going to be L of x equal to your y value, f of a, plus your slope, f prime of a, times your x minus your x coordinate, which is x minus a. Which again, I don't think you should really memorize this, because you already know what they're asking you for. They're asking you to find the equation of the tangent line. You already know how to do that. So this is just a slightly different way of writing it than we might usually write it. All right, I should stop talking because it's 11:52. I should have stopped talking 2 minutes ago.